8 minutes of 502 errors after a simple rollout. The app took 45 seconds to warm up, but Kubernetes added the pod to the service endpoints after just 5 seconds. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover Kubernetes pods deployments. Kubernetes is an open-source platform for automating deployment, scaling, and management of containerized applications. It treats a cluster of machines as a single pool of resources, scheduling containers based on desired state and automatically healing failures. The core primitives are pods, deployments, and services. A pod is the atomic scheduling unit. It can host one or more tightly coupled containers that share the same network namespace and volumes. Pods are ephemeral. They are never repaired, only replaced. For production, always use a deployment to manage pods. Here's a basic pod manifest. It defines a single container with resource requests and limits. Note that this pod is not managed by a deployment. If the node fails, this pod is gone forever. Use this only for local debugging. A deployment is a high-level controller that ensures a specified number of pod replicas are running. It creates a replica set, which in turn creates pods. If a pod fails, the deployment controller notices and schedules a replacement. It also handles rolling updates and rollbacks. This deployment manifest declares 3 replicas with a rolling update strategy. The template defines the pod spec. Note the max surge and max unavailable parameters that control rollout speed. We'll cover probes next. Kubernetes provides 3 probe types. Liveness probes restart the container if it's deadlocked. Readiness probes control traffic flow. If they fail, the pod is removed from service endpoints. Startup probes delay both liveness and readiness checks for slow-starting applications. Here's a production-ready probe configuration for a slow-starting app. The startup probe allows up to 300 seconds for boot. Once it succeeds, liveness and readiness probes begin their normal checks. This prevents premature restarts and traffic routing. Kubernetes supports 2 update strategies. Rolling update replaces pods incrementally, maintaining availability. Recreate terminates all old pods before creating new ones, causing downtime. Choose based on your availability requirements. The first manifest uses rolling update with max surge 25% and max unavailable 0, ensuring 0 downtime. The second uses recreate, which will terminate all pods before creating new ones. Use recreate only when you can accept downtime. Every container should specify CPU and memory requests and limits. Requests guarantee minimum resources for scheduling. Limits prevent a container from consuming all node resources. Kubernetes assigns Co-S classes based on these settings. The first pod has requests equal to limits, giving it guaranteed Co-S, most predictable performance and last to be evicted. The second has requests less than limits, making it burstable. Avoid best effort, no requests limits in production. Best practices: monitor resource usage for at least 7 days, set requests to the 50th percentile, and limits to 1.52x the 95th percentile. Use guaranteed Co-S for critical services. Enforce namespace-level quotas to prevent runaway resource consumption. This deployment shows per container resource settings. The main app and sidecar have different profiles. Always set resources for every container and use different values based on each container's needs. Production operations go beyond kubectl apply. Use kubectl set image to trigger a rolling update, rollout status to monitor, rollout undo for instant rollback, and rollout pause to test a subset of new pods before completing the rollout. These commands are essential for managing deployments in production. Use rollout undo for instant rollback and rollout history to find a specific revision. Scaling is straightforward with kubectl scale. Kubernetes can auto-rollback if you configure progress deadline seconds. When a new pod fails liveness or readiness within that window, the deployment controller reverts to the last stable revision. Ensure your probes are accurate and test rollbacks in staging. This deployment has progress deadline seconds set to 120 seconds. If pods are not healthy within 2 minutes, Kubernetes automatically rolls back to the previous revision. Keep at least 10 revisions for safety. CPU-based auto-scaling is often misleading. Instead, use application-level metrics like HTTP requests per second or queue depth. Set min replicas to at least 2 for redundancy and use stabilization windows to avoid flapping. This HPA scales based on HTTP requests per second, a custom metric. It scales up instantly, but waits 5 minutes before scaling down. The min replicas is 2 to avoid single points of failure. Services provide a stable network endpoint for pods. They use label selectors to route traffic to healthy pods. Pod IPs change on restart, so always use a service for communication. Common types include cluster IP for internal and load balancer for external. This service selects pods with the label app, payments, API, and exposes port 80, forwarding to port 8080 on the pods. The type is cluster IP, making it only reachable within the cluster. ConfigMaps and Secrets separate configuration from the immutable container image. ConfigMaps store non-sensitive data like URLs, while Secrets handle passwords and tokens. Use nfrom to inject them into pods without cluttering the spec. Here, a config map and secret are created and then injected into a deployment using nfrom. This keeps the deployment manifest clean and makes configuration changes easy without rebuilding the image. The pod template inside a deployment is the blueprint for all pods it creates. To update the application, edit the template, never the running pod. The replica set ensures all pods from the same template are identical. The template section defines the pod spec. Any change here triggers a rolling update. This ensures all pods are created from the same definition, preventing configuration drift. Every pod gets a unique IP address, but these IPs change when pods restart. Containers within the same pod can communicate via localhost. For interpod communication, always use a service for a stable endpoint. This service provides a stable DNS name for pods with label app, web. Instead of using pod IPs directly, clients should use the service name. This ensures connectivity even after pod restarts. This is the same issue we highlighted at the start. Here's exactly why that happened. The deployment had no startup probe. The Java app took 45 seconds to warm up its Hikari CP connection pool. The Liveness probe, with initial delay seconds of 10, killed the pod after 3 failures. Traffic shifted to remaining pods, which also failed startup, causing a cascade of 502 errors. The fix was to add a startup probe with failure threshold, 60 and period seconds, 5, allowing up to 300 seconds for boot. This gates Liveness and Readiness probes, preventing them from firing during startup. The pod is only added to service endpoints after the startup probe succeeds, eliminating the error window. Without a startup probe, the Liveness probe begins checking immediately. For slow-starting apps, this causes premature restarts. The fix is to add a startup probe with a high failure threshold to delay Liveness and Readiness checks until the app is ready. If a Liveness probe checks an external dependency like a database, a slow database can cause the probe to fail, restarting the container and increasing load on the database. Use Readiness probes for dependency checks instead. A Readiness probe with a short initial delay can mark a pod ready before the application is fully initialized. This causes traffic to be routed to pods that aren't ready to serve, resulting in errors. Always use a startup probe for slow-starting apps. The startup probe field used in this article graduated to GA and Kubernetes 1.18. If you are running an older cluster, pre-116, the field is unavailable. Always verify your cluster version with kubectl version before relying on startup probes. The article mentions progress deadline seconds, but does not show a concrete example. This snippet demonstrates a deployment that automatically rolls back if the new pods fail to become ready within 2 minutes, using progress deadline seconds and a tight readiness probe. Production caveat: resource quotas block rollouts. When debugging pod and deployment issues, start with kubectl logs to see application output. Use kubectl describe pod to check events and probe status. For rollout issues, use kubectl rollout status. Monitor HPA with kubectl, get HPA-W. Let's run through some common interview questions. What is the difference between a pod and a deployment? A pod is the smallest deployable unit. A deployment manages pods via replica sets, providing self-healing and rolling updates. How do Liveness, Readiness, and startup probes differ? Liveness restarts dead containers. Readiness controls traffic. Startup gates both during boot. What happens if max surge and max unavailable are both 0? The rollout blocks forever because it cannot create new pods, no surge, or terminate old pods, no unavailability. And a few frequently asked questions. Why should I never create pods directly in production? Direct pods are not self-healing. If the node fails, the pod is gone forever. What is the recommended CoS class for critical workloads? Guaranteed, requests == limits for predictable performance and highest eviction priority. How can I test a rollout without affecting all users? Use kubectl rollout pause after creating one new pod, test it, then resume or undo. To summarize, pods are the atomic unit but are ephemeral, always used deployments. Startup probes are critical for slow starting applications. Set resource requests and limits for every container, and always use services for stable networking. Ready to go deeper? Up next, Kubernetes services and ingress, then Kubernetes ConfigMaps and Secrets, then Kubernetes stateful sets. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.